Assalamualaikum to the Sir Lokman. Today, my group will present our project titled Single Axis Closed Loop Position Control System for UAV Antenna. The objective of this project is to design and analyze a closed loop position control system using a MATLAB and a Simulink. Our system focuses on ensuring that a directional antenna mount on a UAV can continuously point toward the target direction even when the UAV is moving. So we go to the second slide to understand why this system is needed. Imagine a UAV flying with a wild communication with a ground station. During flight, the UAV constantly experiences disturbance such as wind, vibration, and changes in direction. Therefore, instead of controlling the antenna manually, we use a closed-loop feedback control system. The controller continuously compares the desired antenna value with the actual antenna position. If there is an error, the controller automatically adjusts the motor until the antenna returns to the correct direction. So, we go to the number 3 slides. System parameter. Next, there are the system parameters. Before designing the controller, we first define the physical properties of the system. The actuator used is 24 volts DC motor with a maximum of 48 watts and a no load speed of 1000 kilo RPM. The armature resistance is 3.5 ohms. For the antenna, we assume a mass of 250 grams and a length of 30 centimeters. Besides the hardware specification, we also define the desired performance. Our design targets are steady state error must be less than 5 degrees. Maximum overshoot should be below than 5%. And lastly, settling time between 0.5 to 0.75 seconds only. These slides show a closed loop block diagram of our system. The process begins with the reference input, which is the desired antenna angle. Second, the controller compares this reference with the actual antenna position received from the feedback sensor. And then, the difference between them is called error signal. The controller then processes this error and sends a control voltage to the DC motor. The motor rotates the antenna until the error becomes as close to zero as possible. This continuous feedback process allows the antenna to maintain the correct orientation even when the disturbance occurs. Next is the extraction of the physical parameters required for mathematical modeling. First, we calculate the moment of inertia represented by J. This parameter describes how difficult it is to rotate the antenna. The larger the inertia means the motor needs more torque to accelerate the antenna. Next, we determine the motor constant, which is Kt and Ke. These constants relate to the electrical energy supplied to the motor with the mechanical output produced. Finally, we calculate the viscous friction coefficient B, which represents the energy loss due to friction inside the motor. These physical parameters are essential because they form the foundation of our mathematical model. So, the next slide is analytical derivation. Using the parameters obtained earlier, we derive the mathematical model of the DC motor. First, we apply the Kirchhoff voltage law, or we call it KVL. to describe the electrical behavior of the motor. Then we use the Newton's second law for rotational motion to model mechanical dynamics. After combining both equations, we apply the Laplace transform to convert the differential equation into the algebraic equation. See, there's a lot of mathematics. So this will simplify the analysis and allow us to obtain the open loop transfer function. This transfer function represents the relationship between the motor input voltage and the antenna angular position. It is also served as a mathematical model that will be used in the next stage to design the controller and evaluate the system performance. This concludes my presentation. Next, I would like to invite my teammate, which is raesul, firdaus, to continue the controller design and the simulation results. Thank you.
So now we continue with MATLAB and system analysis. To comprehensively evaluate the design single-axis height gain directional antenna tracking system for the UAV, the complete closed-loop model and execute with the MATLAB environment. This section details the verification script, implementation step, numerical result, and physical hardware concept validity. And for the simulation result and numerical analysis, the closed-loop tracking architecture was simulated across the comprehensive operating environment distinct angular step maneuver 10, 10 degree, 35 degree, 15 degree, and 75 degree. The resulting tracking profile especially demonstrate successful position tracking performance with optimal damping qualities. The numerical output data obtained from the simulation validates and effectively for the design parameter. The system exhibit an identical peak overshoot 4.6 regardless of the regular step magnitude because the system model a highly linear operating range before reach absolute physical saturated boundaries. This value perfectly match the design specification, which is less than 5. For the electrical margin verification, under the most strenuous tracking maneuver, the linear peak control voltage is restricted to 20.94. Leave an extra voltage margin below the maximum supply seal, which is 24 volt. The corresponding maximum peak instantaneously electrical power draw is 9.54 operating, operating with a heavy safety margin well inside the 48 watt limit. So this is the design performance verification summary. First, we have a maximum overshoot, which is asking for less than 5%, and we get 4.6. The next is settling time, which is require 0.5 until 0.775, and we get 0.544 second. The next is steady state error, which is asking for less than 5, and we get 0. After that, a peak control voltage, which is asking for 24 or less, and we get 20.94. And the last one is control power, which is 48 and less, and we get 9.54, which is all pass. So for the conclusion and recommendation, a PID controller was designed and implemented for the single-axis UAV antenna position control system. The simulation result achieved maximum overshoot 4.6, satellite time 0.5, and 0 steady state. A controller also satisfies the voltage and power constraint of the system. Therefore, all specific design requirements are successfully met. So to further enhance the performance and for the control system in the future design, we recommend to implement the synthesized PID controller parameter on the microcontroller unit and test using HIL simulation or simulate block to evaluate real-world sample rates. After that, maybe we can integrate an explicit anti-wind-up clamping or back calculation mechanism with the PID algorithm to maintain loop stability if extreme external wind gas drive the control voltage beyond the boundaries. Last one, to consider alternative advanced control architecture such as fuzzy logic, linear quadratic regulator, or steady space control for future multi-axis performance optimized and power minimization. I think this all from us. Thank you.